Maybe we can get started for our next talk. The speaker is Matt Kerr, and he will speak on 2 vignettes on hypergeometric normal functions.
Okay, can everyone hear me? I'd like to thank very much the organizers for the invitation, and thank Phil especially. I was Philip's student many years ago at Princeton, and I always thought of him as the intellectual heir to Poincare and Lefschetz. But through so his advisor was advised by Littlewood, Cambridge, so there's a connection to the number theory school there. And so I thought about titling this talk, "What does Lefschetz have to do with Ramanujan?" So that's maybe the subtitle of the talk. So here, when I say Lefschetz, I just want to clarify what I mean, maybe for the students in the audience. It's the connection between normal functions in a family and Hodge classes on the total space. So, I mean, this story begins with Poincare, of course, who was trying to prove what became known as the Lefschetz 1-1 theorem. So if you have a divisor on a curve, that gives rise to a point on the Jacobian torus. And conversely, you can go back using Jacobian version from point on the Jacobian to a divisor of degree 0. And now if you do this in families, if you let the curve vary, then if you have a family of divisors of 0 cycles on the curves, that gives you a section of the Jacobian bundle over the base. And conversely, if you have a section of the Jacobian bundle, which is called a normal function, then you go back fiber-wise by Jacobian version to get a family of cycles on those curves, which stitch together to give a 1 cycle on surface if the curves are fibering down the surface. Well, what's missing from this picture is how you get from a Hodge class, a 1-1 rational class on the surface that you're fibering out by curves, to a normal function in the first place. And that's what Lefschetz did to complete the story. And there are several ways of seeing this, and I'll maybe postpone it until I get to that part of the talk. But that's sort of what I mean by, that's what Lefschetz means to me in this particular talk. It's the connection between normal functions in a family and Hodge classes on the total. On the other hand, if I'm trying to relate Lefschetz to Ramanujan, Ramanujan as a term is standing in for identities and function theory of hypergeometric functions in one variable. So the simplest kind. And this talk is sort of a light spin-off of work that I've been doing with Vasily Golyshev, leveraging this connection, Lefschetz, so to speak, to study conjectures in arithmetic geometry. So Bergström and Dyer, and his generalizations, valence conjectures, block-out conjectures, and to do this in families. So it only makes sense for a variety over Q, but you can try to do it all at once for a bunch of varieties over Q by doing it or calculation in a family and then specializing to rational fibers. Okay, so I want to begin with 2 questions. The first of which was inspired by a talk that John Voigt gave when he came to visit WashU recently. And that is, where do upside down Ramanujan identities, like these 2, which you can find in papers of Jesus, Guillera, and Casey Hall, really come from? So they're called upside down because the right side up would be to have the Pochhammers in the numerator. And the mysterious part of these maybe is the polynomial part of the numerator. So for those not familiar with the Pochhammer symbol, they're just the rising factors. A sub n is a times a plus 1, a plus n minus 1. And then the second question that I'd like to ask is, well, most hypergeometric functions are transcendental. But once you have one like that one, which is algebraic over QZ, it turns out that its exponential integral is algebraic as well. So structurally, why should this be true? And the proofs that have appeared in the literature of this sort of thing have all used complicated chaotic analysis. So as we'll see, it's a simple fact about normal functions, very simple stuff. So that particular example actually appears in papers by recent papers by Zagier and Renato Rodriguez-Villegas. So as I said, we can treat both questions in a way which illustrates the basic connection between normal functions in a family and Hodge classes on the top. Okay. So what do I mean by normal functions? I'm going to start with just a one variable family of varieties of some dimension L. Okay, so in fact, I'm even going to take them to be over a punctured projected line with variable z. And then I just consider the L cohomology of the fibers. Sorry, there are typos because I made these slides today. So I take a subvariation of the family of cohomologies of the fibers, and that's going to be the variation of Hodge structure that I consider. In particular, I want to take something irreducible of level L in this L. Okay, so this is a little bit formal, but the normal functions that I'm interested in are going to look this way. So they're going to be extensions of admissible variations of mixed Hodge structure. You don't have to know what that means, but just imagine you have a constant mixed Hodge structure, or pure Hodge structure really, of type PP on the right, that's the Q minus P. And then you have this H of weight, well, it's got to be weight less than 2P, so L has to be less than 2P. And then you have this E in the middle. So it's some variation of mixed Hodge structures which has only two weights. And the weight 2P part isn't very interesting, it's just taking. This is exactly the sort of thing that you get when you do divisors on a curve. So for example, if I have Q of minus 1 and H is H1 of the curve, then the E would be H1 of the curve minus the support of the divisor, or something inside of that. Okay. So you can reduce this E actually to thimble intervals in the sense of functions. So these are elements of a group of admissible normal functions. And this bracket map is the map that tells you the topological class of the normal function, which tells you it's monodromy. But there's also recovers its infinitesimal invariant everywhere. And so you get something that's both rational and of type BP. It's an H1 of U with coefficients in H. So it's H1 of U with coefficients in H here. We can also do IH1 if we were talking about normal functions with no singularities. This is an interesting sub inside the cohomology of the total space. Okay. Anyway, the admissible normal functions identify with the Hodge classes in this part of the total. Okay, according to the valence and Hodge conjecture, the elements of this group should each correspond to a generalized cycle. What I mean by generalized cycle will come in a moment. But in what sense are they functions? These are just elements of the group. So what we do is we consider just the p-take twist of the sequence that I had previously. And now you consider the trivial element, well, not trivial, generator one on the right-hand side. And you can lift this in two ways to the middle. You can lift it while remaining in F naught, in the sense of the Hodge filtration. Sort of holomorphic lift. That's EF. You can also lift it to EQ in the local system, locally everywhere. And now, since their difference, it's the difference of things going to one, right? Their difference goes to zero, so it comes from HP. But there's ambiguities in each of the lifts. And so you have to go modulo differences in choices of EQ, that's the H of P, where H is the local system, the Blackboard H, and the differences in lengths of holomorphic lengths EF, that's the stuff in FPH. And so you get an element of the Jacobian. So this is one way of thinking about lifting Hodge classes on the total to sections of the Jacobian level like this. So there's a basic sequence of mixed Hodge structures that tells you how to compute the Hodge classes in H1 and UH. And on the left, you have IH1 of P1H, which are the classes that extend in a nice way across the functions. The sections that don't extend in a nice way across the functions have residue maps to the right-hand term, which is the direct sum over the function, sigma, of the monodromy covariance in the limiting mixed Hodge structures at each of those functions. And then you do a take twist by -1. Okay, that adds 1, 1 to its Hodge type. Hodge classes on the left-hand side are going to correspond to families of K-naught cycles. So that's the usual situation, like divisors on curve, on a family of curves, 1 cycles on a family of 3 folds, things like that. That's K-naught, usual algebraic cycles. Hodge classes on the right-hand side, on the other hand, are clearly going to be some kind of algebraic cycle, or some kind of normal function that's singular in codimension 1. As we know, if for those of you who have studied singularities of normal functions and the screen program, that doesn't happen for usual algebraic cycles. It happens for higher cycles, so K1, K2, K3, where you can think of higher cycles as really relative cycles on X cross affine space relative a sort of boundary for affine space. So model for this is you take P1, you remove 1, and then you go relative 0 to infinity. And you can take several copies of this Cartesian product of, say, R copies of this, and then you do relative cycles on X cross that object. And that gives you algebraic KR. That's your Q. Modern way to think about that is in terms of blocks higher Chow cycles, and then you can do torsion, do integrals. Okay, it's easy to compute the ranks of functions. So little IH1 of P1 with coefficients in H is given by the Poincare. So you take the sum of the drops at the punctures, where the drops are the numbers of non-invariant cycles at that point, and then you subtract off the rank of the base times the other character, rank of the variation times the other character's base. And you want situations where that is a very small number, so that you know right away it's got to be Hodge. And that will give us hypergeometrics. The corresponding normal function is non-singular at sigma if the Hodge class maps to 0 there in B. Okay. And normal function is singular only in a subset of the discriminant locus, define a subgroup A and F mu naught H and P. Which is isomorphic to IH1 mu naught H Hodge classes. Okay, you need the IH1 so as to control how they behave in the functions, and that was the original reason for Poincare to call these things normal functions. You want logarithmic growth boundary, and that's essentially what the IH1 is. Okay. So finally, there's a connection to differential equations, which I guess wasn't really noticed until relatively recently, with the exception of one case, and that was old work of Munning in the 60s. So let's assume that the rank of the top piece of the variation, the top Hodge piece, is 1. So I have a Hodge line though. And also assume that each local system has maximal unipotent monodromy at 0. Okay. So the limit mixed Hodge structure is Hodge Tate. So think of this as like a Calabi-Yau variation. Leading Hodge number is 1. Now I take a section over all of P1 of the Delinean extended Hodge line, and take that section to be a generator on A1. In other words, away from infinity. So it's the divisor of this section is all bunched up at infinity. This is just my way of normalizing. And then take L to be its Picard-Fuchs operator. Okay. Obviously, that's not polynomials in D and C or Q bar because they don't commute. But anyways, Picard-Fuchs operator, killing periods in mu, and let's say it's of degree D. So the order is the rank of H. The degree is something else. That's the degree in Z. D. Okay. The highest power of D appearing is just going to be a rank H. The highest power of Z appearing is also this. Now, finally, you take an invisible normal function, for which I'll usually use the notation U, and assume that it is non-singular on GM. Okay, and now I take a multi-valued holomorphic function on U by lifting U. Remember, U is a section of subfamily of Jacobians, so I can lift it to the numerator locally everywhere. Some way. Call that U tilde, and then I can pair that U tilde with the section of the Hodge line, which is like a family of holomorphic forms. So I'm pairing by these brackets, which is like wedge and integrate, essentially, over y. The lift of the normal function with the holomorphic form, and I'm calling that V of t. That's some multi-valued function on U, holomorphic. And then there's a theorem that I proved with Vasily Golyshev and Sasaki, which says that if you apply L to this V, which kills the ambiguities, by the way, coming from the local system and from the FP when you lift U. This does not depend, this G does not depend on the choice of lift. So this is a polynomial of degree less than or equal to D minus the degree of the extended Hodge line. Okay. That's often very small. And so this is very good for practical use. If you want to compute the inhomogeneous equation of the normal function, you only have to compute the first few terms of, say, power series expansion of V to get what this G is. Moreover, Z divides G if U is not singular at the origin, and G has coefficients in Q bar if U comes from a cycle. Okay. If U arises from a cycle, by which we mean you're taking fiberwise Abel Jacobi, you're slicing the cycle lives on the total space, you're slicing it by a fiber of the total space by our projection. And then you are doing Abel Jacobi fiber by fiber to get the normal function. In that case, we'll just write mu Z. Okay, so hypergeometrics. So these are ubiquitous. They come up all over the place when you're studying Landau-Ginzburg models, for example. We'll talk about this morning. And they're simple enough that we can compute everything. They're given by data, where you just take 2R rational numbers between 0 and 1, possibly including 1. In fact, we take the last beta always to be 1, so that we have at least one power series solution. And as you'll see in a moment, and none of the alphas equal any of the betas. We're usually going to require that these two polynomials, Q infinity and Q0, also are rational, which is to say that the hypergeometric indices alpha 1 through alpha r and beta 1 through beta r are balanced in some sense. Okay, so you could do like alpha equals 1/5, 1/6, 5/6, right? You could do alpha equals 1/5, 2/5, 3/5, 4/5, something like that. And then the theorem, actually, I should say that, John is here. So John Morgan and Chuck Duran did a classification, a beautiful classification of Z variations in Hodge structure, polarized Z variations in Hodge structure over P1 minus 3 points that satisfy certain properties that you want from mirror symmetry. And they got a list of exactly 14. which had been obtained in, they got a list of 14 that had already been obtained by Fernando de Legos, but what they also did was they refined the classification to over Z, where it's more subtle. So a theorem that I'm going to attribute to lots and lots and lots of people, probably not enough. Berkers, Heckman, Katz, Alessio Cordia, Vasily Golyshev, Roman Fyodorov, recent work by Abdel Raouf and Bugiati, probably people I'm getting, but basically there exists a rank R motivic Q polarized variation of Hodge structure H alpha beta over P1 minus 3 points, whose Picard-Fuchs operator looks like that with the alphas and betas, and has period the hypergeometric function corresponding to the indices. So here you have the Pochhammer for the alpha j's over the Pochhammer for the beta j's, producted together, and that's your power series. There's also a beautiful Hodge number formula. Oh, the other person I should mention is, people I should mention are Fernando Villegas and David Roberts, who wrote a beautiful notices article that explain this Hodge number formula, which is given by these zigzag diagrams. Makes it very easy to compute with the Hodge numbers. I'm just going to tell you two factoids about what they are in two special cases. If all the beta i's are 1, then the Hodge numbers are all 1. Okay. So it's like a principal Calabi-Yau variation. And well, if the alpha and betas are completely interlaced, so an alpha follows a beta, follows an alpha, follows a beta, going around the unit circle, it's a model for 0, 1. Then actually the monodromy is finite and the variation has level 0. It's sort of isotrivial, stupid variation, but still interesting. So the monodromy, in the interlaced case, it's finite, but could be quite interesting. Otherwise, it's a full symplectic or full special orthogonal group. And if all of the beta i's are 1, you get maximally unipotent monodromy at 0. More generally, Q naught and Q theta or Q infinity are the characteristic polynomials of the monodromies about 2 poles, 0 and infinity. And the rank of T1 around 1 minus the identity is 1. There's 1 vanishing cycle, so to speak. If we drop the Q rationality criteria at the top, then you still get a variation of Hodge structure, but it's a K variation of Hodge structure for some abelian extension K of Q. And then you can do restriction of scalars down to Q to get a larger rank variation. Which, when you tensor that up to K again, splits into a bunch of pieces. K variations of Hodge structure, which are conjugate, and you can say exactly which hypergeometric indices those correspond to. Basically, you take your alphas and betas in that case, multiply them by various Ks, and then that's a fractional words. Okay. Finally, there's a gadget called Frobenius deprivations. So this is a generating series of some kind. Probably everyone, probably most people in this room have seen the trick where you take something like some 2n choose n squared z to the n or something like that. Then everywhere you see an n, you add plus 2 epsilon, plus epsilon, like that. And then in this particular case, what you would do is you would differentiate ones with respect to epsilon and set epsilon equal to 0. And that gives you the other period of that hypergeometric variation of Hodge structure. In fact, it gives you, if you do it right, it gives you Q-Betty periods. It gives you exactly the correct thing. So indeed, it gives you some sort of generating series of solutions to the Picard-Fuchs equation. And when you apply the operator L to it, you get z to the s, which you should think of as e to the s log z, times some polynomial in s. And if you specialize to s equals 1 minus beta j, you actually get solutions to the correct operator because you kill off that polynomial at Z0. And if a beta j is repeated, then you need to differentiate with respect to S. Take the partial derivatives as many times as you have repetitions of that beta j to get additional periods. Those periods will have log squared, log cubed, and so on. One reason that one likes hypergeometrics is by the Euler-Poincaré theorem, little IH1, GM comma H is 1. So you get a Tate Hodge structure. The weight of that Tate Hodge structure is controlled by the number of beta j's that are equal to 1. And in any case, we get an automatic normal function. Okay, so case in point. Any questions on hypergeometrics? So I want to explain where the identities in the beginning came. Start with a variation over a Zariski open in P1, which we take to be as usual of weight L. Here L needs to be even. Think family of 4 folds or 8 folds or something like that. And the Hodge numbers should all be 1. So the 4th or 8th cohomology respectively doesn't have to have Hodge numbers all 1, but there should be some subvariation that does. And now I take an admissible normal function on P1 minus, well, on U really, but with no singularities away from 0. And I want it, I'm choosing L plus 1, which is a very high choice of weight. And that ensures that I will produce a normal function k L plus 1 times. So this is inherently a higher normal function in the sense of not being classical, not being k naught. And now I take a lift of the normal function from its Jacobian bundle up to just the bundle of cohomology, and I pair it with the section U of the Hodge line, as before. So that gives me my multi-valued holomorphic function. And now I suppose that I have a particular point in the family where I get a new Hodge class. So if I have a family of Calabi-Yau 4 folds with Hodge numbers all 1, then I go from my Hodge structure type 1, 1, 1, 1, 1, and the middle one suddenly splits off and becomes a Hodge class at this point Z naught. Okay, I'm not yet assuming that it's represented by an algebraic cycle, but in that case, there exists some polynomial of degree m such that if I take that polynomial and I shove nobla d, where d is z d dz, into that polynomial and apply that thing to the section of the holomorphic forms, then at Z naught, that will give me my Hodge class to the power of 2 pi I. Okay, now suppose everything is motivic. So my Hodge class is represented by W in Chow M X Z naught defined over Q. We can talk about what happens when it's not defined over Q, but let's just stick to this. And then mu equals mu Z, or this higher Chow cycle. Type L plus 1, L plus 1. Then it turns out that P will be in Q of Z. So this is one of those typos that happens. So P is in Q of Z. Z is, so what is this AW? It's the structure map going from W to a point over respect Q. So we're pushing down the specialization of our cycle on this higher cycle on the total space. So what have I done? I've specialized the higher cycle on the total space to the fiber X Z naught. Then I've restricted it to W, and now I'm pushing it forward to a point over Q. That gives me a cycle of type Chow n plus 1, Q2 n plus 1, where Q means spec Q. And our Jacobian such a cycle by Borel's theorem is a multiple, a rational multiple of the n plus first odd zeta value. Oh, sorry, not odd. L is the frequency. So what's on the left here, we p of d applied to the multi-valued holomorphic function, specialized at z naught. That's the same thing as the lift of the normal function at z naught, paired with 1 over 2 pi I to the m times the class of w. Okay, and now I'm simply saying that that pairing inherently restricts z to w and pushes forward. Okay, so it's basically this trick with Borel's theorem that's telling us that something gives a zeta value. Okay, and that will be an identities. If we don't know that C is represented by W, then an identity of this type gives strong evidence for it. Okay, because you cannot make this conclusion if C is not represented by an actual algebraic cycle. On the other hand, we typically do know 2. So what kind of cycle is this? This Z. If X arises from level sets of a Laurent polynomial in a torus, as in a Landau-Ginzburg model, you just take the coordinates of the torus and you restrict those to X. And then you think of that restriction as being the graph of those L+1 functions over X inside X cross affine L+1 space. That's hypergeometrics. Okay, hypergeometric case. Suppose H is hypergeometric with all the beta j's equal to 1, then IH1 of GMH is a cube minus L minus 1. And there exists a unique normal function on GM valued at H, and it's of the desired type. Okay, so this is one thing hypergeometrics give us. The second thing is that my theorem with Golyshev and Sasaki tells you immediately that inequality that bounds the degree of N over G is termed, the right-hand side is 0. So LB has to get a constant. And setting now L hat equals L composed with multiplication by 1 over C gives L hat CV is 1. Why I did that, you'll see in a moment. Since all the alphas belong to the open interval 0, 1, there exists a unique single value determination of B about infinity. Because you can change B by a period, but there are no periods that are invariant about infinity. They all have some weird eigenvalue. Now, taking W equals 1 over Z, L hat gets rewritten as what looks like a hypergeometric operator just about infinity instead of about 0. And that thing kills Z times our section of the Hodge line. There's also a corresponding Frobenius deformation phi hat, which is sent by L hat to Z to the S times polynomial S as before. But now notice the alpha j's are in the denominator instead of the numerator. And now setting S equals 0 kills the Z to the 0, which becomes just 1, and makes the polynomial part a constant product of alpha j's. So dividing by that, I get that phi hat of 0W is the unique solution of L hat equals 1 about infinity. And so I have an explicit formula like that. And since 1 over W times V, CV is also a solution to L hat equals 1, that means they have to be the same. So we have explicitly identified our multi-valued holomorphic function as a single-valued function about infinity, uniquely. And when we apply P of D to it and specialize to W equals W naught, we get the identity that we're after. And the ones that I showed at the very beginning, like Guillera and all, correspond to families of Calabi-Yau fourfolds and Calabi-Yau eightfolds. So Vasily Golyshev and Mohammed Elmi have carried out a robust computer search for some families of Calabi-Yau fourfolds, at least, trying to identify all Hodge points. There aren't very many, at least they can find. And all of the identities that come out of their search appear in papers like Guillera's. And so I regard that as a good thing. That's evidence for the Hodge conjecture, right? Because every time there's a Hodge point, you get one of these identities that's been proved by completely different techniques. And that can only be true if the thing was represented by an actual cycle. There's a related perspective on the Gross-Sagier conjecture. And so I'll say what that is in a second. Over a modular curve, you have a family of Picard 19K3s with H equals H2 transcendental. So that's a variation of Hodge structure with Hodge numbers 1, 1, 1. Okay. If there are no weight for cusp forms with respect to that gamma, then every CM point in Y Q bar yields a normal function mu tau K1 type. Okay. So I mean, you just show directly that there is a Hodge class on the total space of family of K3s minus that CM fiber. And it can only come from a K1 cycle, not a K0 cycle. Pairing this with a section of H11R, so there's a canonical section, sort of omega wedge omega bar type of thing. This gives V tau a higher grade function. So it's like the V that we had before, except it's single valued this time. And now you pick any other CM point tau prime, and by Lefschetz 1, the extra Hodge class on X tau prime is algebraic. So it's sort of the reverse of the situation we had before. We had before a normal function, which we know comes from a cycle, and it's at the Hodge points that we're not sure we have a cycle. Here is the reverse. The Hodge points, you have a cycle by Lefschetz 1. Overall, on the total, we don't know if the normal function of K1 type actually comes from a K1 class. If the valence and Hodge conjecture holds, and that's true, then you can prove directly that V tau at tau prime is a Q-bar linear combination of log of algebraic numbers. And that's the Gross-Zagier conjecture. The Gross-Zagier conjecture, on the other hand, is now a theorem of 3 people. I think I got the names right. I'm not sure about the middle one. Rudy or me again. This gives good evidence for the valence and Hodge conjecture in the same sense. But I think it would still be very nice to prove Gross-Zagier this way, showing that the K1 cycles exist. Okay, so questions before I go to the last part? And 15 more minutes, is okay? Okay. So according to Berkes and Heckman, which was sort of the foundational modern paper, hypergeometrics, beautifully good. Alpha and beta are interlaced if and only if the local system, the hypergeometric local system H, has finite monodromy, which is equivalent to saying it's like isotrivial level 0, which you can put in weight 0 times 0. And that's equivalent to there being a unique single valued solution about 0, or rather, the unique single valued solution about 0 being algebraic over Q and Z. Okay? That unique algebraic solution, up to scale, I normalized it to start with constant of 1. That's the standard hypergeometric function solving for L. So Golyshev conjectured in, well, like 7 or 8 years ago, and then it appeared in a article by Zagier, that the exponential integrals of such algebraic hypergeometrics are themselves algebraic. And that was proved recently by Delay and Ribois using p-adic analysis. But it turns out there's something much simpler you can do. The only question is, what Hodge class do we fiber out where to get a normal function? It's kind of the whole thing. So let's let X be Riemann's existence domain for F, little f. That's given by some polynomial in 2 variables, C and Y. And so you sort of think of this as an algebraic curve fibered out over P1Z, with Y as the vertical coordinate. And since it's an existence domain, well, that means that Y is the thing that satisfies an equation over Q of Z. So Y, restricted to the curve, is the analytic continuation of F. Okay. As to why it's defined over Q, that's simply because that little f has an expansion with rational power series coefficients about a rational. And now I claim that there actually exists a capital F tilde as a rational function in Z and Y, analytically continuing the first branch capital F on X. And moreover, d log of this F tilde is little f tilde dz over z. That's equivalent to saying that F tilde is capital F is the exponential integral of little f. Okay. So X over P1Z is a D-sheeted cover for some D over P1, and that D has to be bigger than R, where R is the rank of the order of the Garten's function. Okay, now the hypergeometric local system HZ, this is the integral lattice, has to be contained in the reduced cohomology of fibers. Okay, so this is like fibers are a collection of points, right? And that's a consequence of integrality of monodromy, something that's proved in numbers. And H1 of the total space, remember the total space is just a curve. And now I'm removing the fibers over 0 and infinity. And I'm looking at H1 of that twisted by 1. Well, that contains IH1 of GM, the coefficients in hypergeometric variation of 1. And as we read before, that has rank 1. And is actually just isomorphic, in this case, to Z of 0. Okay. This is a fancy way of saying we've identified a Hodge class in that X. As an H-valued L2 1 form, F tilde dz over z represents a class in this IH1, and hence has periods in 2 pi I z. We all know what that means. It means when I do the integral, when I do the exponential integral, periods go away, right? It also belongs to omega 1 of h, log of x naught, so holomorphic form of log poles on x naught with res x naught f tilde dz over z, given by the restriction of f tilde to x naught, which is a collection of points over 0. And that's epsilon 1. Okay, epsilon 1, what does this mean? Well, remember, this is the existence domain of the function little f. And so when we analytically continue little f around, it's going to come back to multiples of itself, integer multiples of itself, plus other things, other solutions. Okay, and the integer multiples of itself that appear on some of the points over 0 and not others are going to be the value of f tilde over 0, because all the other things it comes monodromically back around to, which are linearly independent for it, are 0 and 0. Okay, so this epsilon 1 you should think of as a little 0 cycle on this curve that sits over z equals 0, and it has z coefficients. Okay, so the upshot is when I do this exponential integral of little f, I get some capital F because the monodromies go away, and moreover, because little f tilde dz over z had only log poles, and moreover, residue epsilon 1, capital F tilde has divisor epsilon. Okay, so I appear to win, except for one thing. What about the field of definition? Well, to do this, we need to think in terms of normal functions, or at least there's a particularly elegant way to do it using normal functions. So f tilde dz over z is a Hodge class of that IH1. So it produces a normal function with values in h over hz1, which you exponentiate into hz tensor O cross. And that recovers f tilde. Okay? Fiber by fiber. So that right-hand thing basically is the Jacobian. It's a bunch of copies of C star and fiber. Just look at the values of that. And it shows that f tilde has the symmetries of this integer local system with respect to branches of pi. Okay, so what do I mean by this? The one thing that I really mean by this is, well, when you push forward little f tilde, you get 0. You have to, because there's no constant solution of the Cartesian. Well, when you multiplicatively push forward f tilde, the multiplicative version of that is that you get identically 1. So that's sort of taking norm with respect to the projection. And so yes. All right. So this is the point. I'm now going to use this to prove the field of definition. So we could have done everything that I did without normal functions with normal functions, and we get more. Get this nice thing about the compatibility of the local system. So it remains to show that f tilde is in Q of x, rational function field. Its divisor epsilon 1 is defined over Q as a zero cycle. Right? So we may assume that f tilde is in K of x for some finite extension of Q containing Q, say, roots of unity, deep roots of unity, just by specialization. If it was defined over C, I can specialize what's defined over Q bar, and then it's defined over some finally generated extension. Okay, now for sigma in Galois K over Q, we can apply that to f tilde and divide by f tilde. That gives a constant because they have the same divisor, right? Because the divisor isn't moving because it was defined over Q. On the other hand, because the multiplicative push forward of f tilde is 1, that means that d copies of this C sigma to the d, well, that gives 1. And so C sigma is in Q of zeta d, hence in particular in K. And now I just use the vanishing Galois cohomology to say that, well, that C sigma is a one co-cycle in Galois cohomology, but Galois cohomology being trivial, there's some gamma in K, such that sigma gamma over gamma recovers this C sigma, and I can just divide f tilde by that gamma, and that gives something defined over Q, which is invariant of the Galois system. Okay, so tricks with normal functions. Avoid periodic. So simplest example. Alpha is a half, beta is 1, and f is 1 over square root of 1 minus z. The existence domain is this nice conic, and capital F is the exponential integral. It's just 1 minus root 1 minus z over 1 plus root 1 minus z. Notice that when I move between branches, f goes to 1 over f, which is the thing I was saying about compatibility with the hypergeometric local system. And so f tilde is 1 minus 1 over y plus 1 as a rational function. The normal function is log of f, which we can expand about the origin as log of z over 4 plus this this power series. And there's a typo there. It should be 2n choose n, z over 4 to the n divided by n. And Dirichlet's class number formula then says that if we specialize to any Q point in this family, well, many Q points in this family, for any n at least 6 for which n times n minus 4 is square free, I guess you have to start with 7. Writing kn equals q of square root of n times n minus 4, quadratic number field, log of f at 4 over n, so that's special value of the normal function, is this special value of the zeta function of the field, zeta prime at 0, over the class number of the field. Okay, so this is some arithmetic quantity on the right-hand side, and we're saying we have this nice analytic normal function that interpolates it. This is kind of cool. One comment before I conclude, we can generalize the theorem to the unbalanced case, where the rationality of Q not Q infinity is not true, to prove that while the exponential integral of f is transcendental, if you take the sum of f with its Galois conjugates, as it were, its conjugate hypergeometrics, and you do the exponential integral of that, then you still get algebraic things. So generalizing this example, one might ask what arithmetic quantities are interpolated by exponential integrals of, by just integrals, logarithmic integrals of more general hypergeometric periods. Already for the next thing up from the example we just did, log of t plus this series, that gives it a block Kato for K2 of families of elliptic curves. Okay, really mysterious stuff. And one can test block valence in families of Calabi-Yau threefolds using more complicated determinants, hypergeometric expressions. So I want to give you one example Let MT be the hypergeometric motive for alpha beta equals a half, 1, 1, 1, 1. Okay, so that's sort of the generalization that we've been doing. We started with a half, 1, then we did a half, 1, 1, which is the Legendre family of elliptic curves. And now we're at some higher Legendre Claudial free-falls. And now you define these weird quantities, whatever. And now this exploding matrix here. So there's some zeta 3s in here that has to do with the gamma class. So you want to think of these as regulators of two different cycles, where you go between the cycles going from row to row, and you go between the periods I'm taking of them going from column to column. Then L double prime of MT at 0 over R of T, this determinant, can be numerically verified to be a rational number as expected by Valenson's conjecture at these 4 values of T. Also at, I think, 1, 1/4, 1/16, 1/64, I think. But those are symmetric under an involution of families. I didn't write those. And it fails at all the other points. And there's a very good reason for that. Valenson's conjecture says it should fail because one of the cycles does not extend to an integral model. And the matrix entries are periods here of 2 normal functions attached to K4 cycles on a Calabi-Yau threefold family. Okay, so this is an example of what you could do with hypergeometric normal functions. And I don't know if Lefschetz would have foreseen normal functions being used to experimentally verify conjectures in arithmetic geometry, but they proved to be indispensable tool for doing so.